Bonjour à tous. Ce matin, nous avons le plaisir d'accueillir Sebastian Gonzalez, qui est donc ici pour quelques mois et qui travaille alors, entre le musée du violon à Crémone et l'Institut Politecnico de Milan. Voilà. Et donc, il va nous parler de lutherie avec tout ce qu'il fait autour, et donc en particulier intelligence artificielle, machine learning, et puis aussi des métamatériaux et de la mécanique.
Cool. Thanks, Claudia. Thanks a lot for the invitation and for coming. So the title, it was an idea of ChatGPT, but I found it really good because it's from art to science, and instrument making, it's an art. That means it's something that we don't really understand, and understand here is understood as intellectual knowledge of it, because the artists themselves, they can do it. And they know how to do it, but they can't explain it. So I think our job in the lab is try to figure out what they know, but they don't know that they know. Perfect. This is Opa, my ex-grandfather, if you say it like that. It's the grandfather of my first wife. And when I finished my PhD in physics, I went to meet them, and I sat in that little chair there, and I started seeing how he would make the instruments by hand there in this like little workbench and create these beautiful things. And I was like, whoa, this is incredible. Something I want to do. My PhD was in computer simulations, so nothing to do with music. I played guitar back in the day in high school, but I was completely far away from music during my research years. And I decided to learn to work with the wood, like learn by hand. This is a picture of my workshop in Valparaiso. And I think the important thing of working with your hands in instrument making, and this is particularly true for the case of string instruments, where the material is very important. If you play a flute, you can do one plastic, it doesn't really matter, because the interaction with the material is not, it's just the geometry, not the material itself. But wood, it's a very complicated natural material. And you have two pieces, they can look the same, but when you start working with them, and when you work with the plane, this is a Japanese plane because it's a very sensitive object. Oh, yeah, sensitive. To use it, you need to be very focused on what you're doing and in contact with your body. And when you work in this close contact with the material, it reveals things that you cannot see just by looking at them. And this is another quote I like a lot. It shows how the Japanese select the wood for their buildings depending on the location where the tree grows. So there is a saying that you don't buy a tree, you buy the whole mountain if you want to build something. And the Cremonese luthiers, they do something similar, and they go to Val di Fiemme. It's a particular valley in the Italian Alps where this beautiful and marvelous wood grows. And they go to this particular place because it was where Stradivari used to cut the wood. But global warming, the weather is changing, the summers are getting colder, the winter as well. So the wood is growing at a different rate, in a different way. So the wood we have today, it's different from the one of 300 years ago. And this is something that we will try to fix with metamaterials. There is something in the chat. I don't know if... Okay. Oh, perfect. Okay, so where do I kind of see myself in the intersection between science, craft, embodied knowledge of the makers, and artificial intelligence? And I will try to explain how all this comes together in our work. Okay, I arrived to Cremona in 2018 for the Mondo Musica fair, which is like the largest violin-related fair in the world. And I went to the lab, and inside the lab, you can see this picture of the visible and the UV fluorescence of Stradivari violins. And they are all slightly different. weird objects that if you start to look close to them, they like here is like it's here. This is slightly wider and more blocky, and there are subtle variations that influence the way the instruments sound. Or we think that. So when I arrived there, I realized that pictures alone, they don't make it, because the instrument, so I don't have one, but it's a 3D object with a very complicated geometry. So how do we start modeling that? The answer, of course, comes from history. That's a drawing from Enrico Ceruti, luthier violin maker from Cremona in the 1800s. And he puts points, and he draws a violin outline with just a compass and a ruler, which is the traditional way of making architecture till the Baroque period in Europe. And I just grabbed that image that's part of the collection of the museum, put it in the computer, put some numbers, and it works perfectly. You can fit pretty much any maker with a bunch of geometrical parameters. The idea being that if you have a description, a mathematical description of the object, you can train an artificial intelligence to learn whatever you want it to learn. But the first step is turn the object into numbers. And if you are familiar with artificial intelligence, usually you have a picture of a cat, a picture of a dog, and the computer learns this. But in the case of the violin, it's not possible because the picture doesn't capture everything. From the outline, we define the thickness map of the top plate and the back plate as well. And this is an historical example. Citation. And you can see that the color is proportional to the thickness of the plate. This is the bus bar. For those who don't know, the violin plate, the top plate, has the holes and a bus bar, which is a piece of wood glued most of the time. Sometimes it's carved, but that's very bad practice. That's used to reinforce the bass side of the instrument. That's what it's called, bus bar. And the thickness, it's not homogeneous in the top plate. The central part in this example is thicker, and here on the side it's thinner. So what we did was create 9 regions for the thickness of the plate, which is kind of an easy way of reproducing the historical example. The thickness here, it's kind of random, doesn't make much sense, and it's not symmetric. That's especially done so the algorithm, when I train artificial intelligence, learns all the possible ways of making instruments, not just the historically accurate ones. Also, there's 3 different plates show 3 different choices of parameters of the model. So there is one very fat violin, and another that's very thin. And the last one, you're pretty much never gonna find a violin with that shape by an instrument maker. It would not sell. It's too ugly. Once you have the thickness, the last thing that we did, and that was kind of the most difficult part, it's the arching of the instrument. One option is, this is the longitudinal direction. So here the tailpiece, the neck is over there. You can rather easily just fit a polynomial fit to the shape.
Sebastian, maybe you should explain what is arching. So,
perfect. So when, okay, let's pretend this is the violin. Okay, it has 2 sides and it's curved in the longitudinal direction as well as the transversal arching. And these shapes varies along the, just, let's say this is the color is the height of the instrument. it varies in this direction and in that direction. Okay? Well, the longitudinal one, you can pretty easily fit the data with a 6-degree polynomial for both the top plate here on top and the back plate on the bottom. And for the transversal arching, I created a very simple functional model that it just imposes the boundary conditions on the edge and on the center of the arching. I just want a polynomial that it's 0 here, and its derivative is 0 here, and it's 1 here, and the derivative is 0. The solution for that is 1 minus x squared. Very simple shape. And then with a change of variable, I can scale the arching profile along the longitudinal direction to obtain different realistic models of the arching, which in this case is just the polynomial. Here it's a top plate by Stradivari, the Messiah. And this is one of the difficult part of making studies with all the instruments. If you put the strings on a violin, a piece of wood, it will creep, it will move. So it will deform. And the more you play, the more it deforms. It's very difficult to know how like the violin was actually original in the beginning. So making comparisons, it's always tricky. Actually, this is the Messiah. I made a mistake. And this is my model. It's a slightly non-symmetric. Probably because this side has the bus bar, whereas this not, so it has moved a little bit. And on the, that's your right, on the right, it's the back of a Guarnieri instrument, which is slightly rounder and fuller here in the bottom. And we can just varying the shape of the scaling factor obtain these different models. So how does the data set look? That should start moving. We create a lot of artificial top plates. Why top plates? Because A, it's easy. B, it is thought that the top plate is the most important part of the instrument because it's the lightest and stiffer, so it moves more, it generates more sound. And once you have the top plate, you can build the rest of the instrument rather easily. That's a vibrational response, just looking at the eigenfrequencies of the plate. And you can see that in general, they grow. I'm sorting here by the mean frequency of the plates. They grow at the same time that the instrument becomes larger and thinner. But it depends, you can see here, but they have different arching, different thicknesses. So they are not all the same. But there is kind of a trend, like the wider and fatter the instrument is, the lower its response. With this model, like we have a way of turning just like a bunch of numbers, that's the points from the beginning, so geometric parameters, thickness profile, and a given material into instruments, and we do that with like a little robot that cuts the top plate of the instrument. But actually, that's a bad. When we want to, I mean, for this, we kind of optimize to give something reasonable that's usable by a violin maker. Because, yeah, this was wood from the violin maker that I work with, so he wanted to actually carve it.
So you optimize?
No. We just take parameters that look like a historical model. Okay. Yeah, by hand. It's trial and error. It's quite difficult to fit these 20 parameters into one particular. Yeah, to do the data set, we start from we fit by hand, like Monte Carlo by hand algorithm to get the closest approximation to the Messiah, and we vary from there.
The Messiah is one of the most famous Stradivarius.
Yeah.
You could, Messiah, this year, because it's, you know, very beautiful condition.
It was so kind of never played. So
it's a reference in common.
And you can see the, sorry, the difference in the arching profile between the Messiah with the Guarnieri, which is like more crude and like asymmetric. So it's a very good example to work with. Cool. Okay, so with all that, we have a bunch of numbers, 35 numbers or so, that describe the top plate of an instrument. We can put that model in console to do finite element simulations and have the neural network learn this. And the first thing we learned was the frequencies of the first 5 or 10 eigenfrequencies. The architecture of the neural network is very simple. It's just like one hidden layer fully connected, and the prediction power is quite good. It's like really nice fit. The idea is like, okay, artificial intelligence works. That's like, it's not very relevant that it can predict the eigenfrequency because they don't say anything about how the instrument will sound. But if you follow me, we will get to like more interesting stuff. But not only that, like the neural network, since you have a data set to train it, it's a big sample of all the possible instruments, you can do like simple correlation to try to understand what's going on. But the neural network is just like black box that doesn't tell you much. And I think humans like to think more in terms of correlation between things. This, for example, the correlation between the thickness profile and the frequencies of each mode. And the redder it is, the higher the correlation. And there is one thing that's clear immediately, it's that all the frequencies are correlated to the thickness in the central part of it. Why this is relevant? Because instrument makers think that they can tune the plates by just taking a little bit of material in one part of the top plate, so they're going to change one frequency. The truth is that wherever you take some material, you will change all of the frequencies because they are all correlated to the thickness. Also, you can find in this data set very different instruments that are practically, they have practically the same vibrational response. This is in light blue, the whole data set, and the red and black are the two closest curves with the most different parameters. If you pay attention, the red one, it's wider, slightly, but in terms of violin making, it's quite wide. It is a fat violin. The thickness profile is different. So this is thicker, heavier in the center, whereas this is lighter. And this is heavier, like thicker on the top part. And you have two ways of vibrating the same. So what I think this means is like the instrument maker knows how to do with different woods, different shapes, that the thing behaves in the same way. And that's why you can identify kind of the sound of a maker. You talk about the Guarnieri, you talk about the Strat, and the instrument makers nowadays, they talk about the models as having a particular sound, which it actually happens to be the case. What else? We can look at the importance of the different variables. So this may be a very engineering way of looking at the problem. So I separate the outline, the arching, the thickness, and the material. And I vary those parameters independently. So I say, okay, I have this model. What happens if I try all the different kind of woods? Or I have this wood and I try different outlines. And I look at the variation in the mean frequency the mean frequency, it's a good descriptor of the vibrational response because I did the PCA, the composition of the data, and it's like a good description. That it could be the first one also, since they are all correlated. And the wider this distribution is, it means there is the most change in the results. So from here, we find out that the outline and the material are the most two relevant parameters for this. This result is also quite controversial in the instrument making world because violin makers start from a model, they have the outline, and what they change is usually the arching profile or the thickness, but you can only do so much with it. It would be better, and that's the dream of the future. If you have a given piece of wood, you can optimize with the computer the outline to generate whatever response you want. Okay. So we have artificial intelligence working this, and it's able to predict. What's the advantage of it? A, it's fast. B, it's easy to use. You just need a bunch of numbers, like no 3D modeling, nothing, and it gives you a response. So you can do optimizations. Optimizations, like you just have you define a loss function, and you evaluate for different parameters how this loss function evolves. It takes usually a lot of time because it's a multidimensional landscape, so you have to move around. If you do it with FEM simulations, it will take a year. With a neural network, you can do it in minutes or so. And one thing we did was to, for each parameter here, we change it in a random way till we have a variation of 10% in the eigenfrequencies. Just, it's like we start from here, we move in one direction, and we ask, can we optimize the other parameters to go back to the original state? Okay, so it's a way of compensating for variations in my material or in my design. Like if the idea is like, if I have a harder wood, how do I have to change the arching so it behaves as this softer wood with a given arching? And we can do this matrix for all the variables. And we find out that when the outline is optimized, the percentual error in the frequency is below 1%. Whereas if we vary the outline and we try to optimize the other things, the results are horrible. Like in particular, trying to vary the arching to compensate for the outline variation gives you pretty much the same original error.
It means that you cannot compensate.
No. Yeah. One thing here, we're talking about top plates. And when you have a complete violin, if you change the outline, you change the volume, which changes the first air resonance in the instrument, which is like the one that most resonates. So it needs to be taken with a grain of salt, this optimization of like free plates. Okay, same thing here. Like all this was just simulations, and we're actually waiting to do the experiments. That's when we're gonna submit the next paper. We did it for guitars. And instead of using artificial intelligence, we use reduce order model, which is you have the matrices of the FEM problem, and you find a kind of linear decomposition of them into a smaller dimensional space. So you find a mechanical model that's a simile of your real model, which way fewer degrees of freedom. And what we do is we have one top plate that we do experimental model analysis, so we can check the shape of it. We have another top made with slightly different materials. In this case, the top plate was 10% stiffer. That's the difference. The density, we match them. Well, we cannot measure much more. And we optimize the height of the bracings to obtain a top that vibrates the same way as our reference instrument. How we do that, I'm going to skip that. Just go to experimental validation. And in the same way as artificial intelligence, we do we vary randomly the height of the braces, and we obtain the correlation matrix between the height variation in the braces and the frequency variation in the modes here. And we can use that to predict what has to be the height of the braces in the guitar such that the frequencies are the same. But once you feel frequencies, and that's why like makes sense to look at the frequencies for the artificial intelligence, the complete mobility is fit as well. So we have the top one, which is our target vibrational response, what we want to copy, like the Stradivari guitar that we want to make popular. We have a second top that has geometrically the same shape as the first one, but since the material parameters are different, the vibrational response is different, with the purple here. And top two, it's experimentally carved, computer optimized top plate that is supposed to reproduce top one. And you see that the speed is quite good. This peak is perfect. The amplitude here is like different, and here the frequency is very, but then again, that's perfect match. Or as perfect as it's getting in the state of the art. This is our editor. When we submit the paper, it seemed he got sick or something. So after 6 months, he just could not review the paper anymore. And we're still waiting for the answer since October last year. What else? This model only works with this is a model order reduction that only works with affine geometric transformations, which in the case of the height of the bracing, it works. You have the same mesh always, so you can make it larger or shorter. But if you want to control the complete instrument, you need to do like much more complex geometrical changes. And this is currently a master's student working on this, where we have a completely parametric model of the guitar. This is done in Fusion, so once you have the outline, you can obtain the 3D shape. And from the top plate, you just kind of extrude the sides and make the back. And essentially, okay, if each of these points is a set of parameters that you okay, let's see. Adrian Hazelman is a guitar maker in Berlin, probably the best guitar maker that, yeah, he loves to work with double top. It's a top plate that carves the inside of the top. Why this is used? Because you can put in the top without greatly reducing the stiffness of the instrument. So the idea of the metamaterials in wood plate is that by controlling the geometry, you can select what's the stiffness of your material. This is important because in general, you have like, we saw in the example of the guitar here, you have these two guitars, they have the same density, but they have different stiffness. So one option, instead of changing the geometry of the bracing, would be to just make patterns in both wooden pieces, different patterns, to match the base material of the instrument. Okay, what happens when we put this on guitars? This is a 3D picture of the complete instrument. When we change the inside of the top plate, we make little cavities. They are not like true holes because you don't want a Swiss cheese guitar. What happens when you change the hole pattern? This is the solid top plate, the displacement when the strings are connected. Goes up. Depending on the size, that's P, of the holes, you have a larger displacement. So if you're lowering the stiffness, you put a force, your displacement is higher. But this can be easily compensated by just increasing 1 millimeter the central brace of the instrument. So the net gain the net mass reduction is around 10% with the same stiffness in the material. So what is it? P is the size of the hole. So from this is 1, this is the big hole, and P is the factor of the delay. So 0.3 is 30% the size. Smaller. Those patterns can be easily made in a CNC. You program them. Just for the sake of the time, I'm going to skip the von Mises stress, but as one would expect, the higher, the bigger the hole, the more probable it's that you're going to break the instrument. So you have to compensate for things. Okay. Sound, because we've been talking only of eigenfrequencies and vibrational response, like musical instruments sound. Yeah. This is the spectrogram of a cellist student playing the first 4 strings and then a scale. And you can see that, yes, you have the fundamental of the string, but mostly in this case, like the harmonics go well to the 10,000 hertz. So when you play a string in the guitar in this case, for example, A or a B, in French is là and there. What are you seeing actually? You see influence from the vibrational response of the instrument at all these frequencies in a smaller way. The higher you go, the smaller it gets. But you see many parts of the vibrational response of the instrument. So when you change one parameter, in this case, the metamaterial shape in the guitar, the whole frequency response changes. And it means that when I play a string, the sound will change. How do we study that? And this is work with Mark Rao from Stanford. We give him the sound pressure level and the admittance of the instrument as this. And he records a pickup and an electric guitar. And I hope with sound, I didn't share with sound, I think. But that's the guitar solid top. Pattern. So it's kind of a convolution of the pickup signal with the sound pressure level response that you actually can hear the difference. And if you look at this as just raw data, it's very difficult to say like how different it is. But once you hear it, small difference in each frequency will make that the whole sound sounds different. Okay, this is the last example that we have. So we went from violins, classic guitars, archtop guitars. Archtop guitars, it's a mix between the violin and the guitar, in the sense that the body and the bridge are like, well, the body, it has the shape of a guitar. The bridge, it's like a violin. It's not blue. It's put by the force of the strings. The bracing, it's like kind of the violin family, in the sense that there is one bass bar, but in this case, there are two bass bars. The bracing, it's, we call it parallel. It's not parallel, it's like a V. It goes over the bridge in both sides. And the advantage of the archtop guitar is that it's easier to model. It's just like with a few control points, you can create a spline. The arching is also simpler. So we can vary the thickness of the top plate by just controlling one parameter quite easily. And we study the variation in the sound pressure level when we vary the geometry, when we make it thinner or thicker. That's something that guitar makers do. Or when we change the material that we're using. If we use a denser or softer material or a stiffer, denser or lighter material or a stiffer and softer material. This is the sound pressure level for the reference. Can you see the lines? Not very well, no? Okay. The first mode, which is the breathing mode of the instrument, doesn't change much because you're not changing the volume of the box in a significant way. But from the second mode onwards, you see a very clear change in the sound pressure level. This is when you vary the geometry, when you make thinner or thicker the top plate. And look at this mode in particular. Thick moves it to the left, whereas thin moves it to the right. The same happens when you change the density. You have a variation to one side and the other for each of the modes. And the same happens when you change the stiffness. So, and this is like one of the problems of doing experiments in instruments, that you can have the same geometry, you have the same wood, but the slight variations in density and stiffness will move your frequency response toward places that you don't really know how it's going. Okay. So from this, we have the frequency of each note, and as well as the amplitudes of the sound pressure level at this frequency. We have also trained neural networks to learn this, which surprisingly is simpler than learning just the free plate, because since we're only varying the top plate, the effect of the rest of the guitar kind of constrains the response of the instrument. So it makes it easier to learn the variation of the top plate when it's connected to the whole instrument than when it's by itself. And we can predict the amplitude of the peak and the frequencies quite well, except for this weird outlier there. Why this is relevant? Because if we have a way of computing this without going through FEM simulations, this takes 18 hours to run. The neural network takes 0 time because it's just evaluating a matrix. So essentially, it's infinitely faster to do the neural network. And you could have start doing sound design of the instrument. I'm not going to show the sound. We have the same sound files with different chords because it's a jazz guitar, so we play a G13. And we study the spectrum of these generated sounds. And we can look at, for example, describing the spectrum of an instrument is very, very complicated task. But one descriptor used in the literature is the spectral centroid of a sound that relates to a timbre. And we can see how when you change the material, in the case of the density of the top plate, rather nothing happens, which was quite surprising. But the stiffness of the top plate has the most relevant effect, together with the geometry. So geometry first, stiffness second, density doesn't change much. I have the files if you want to hear them. And this is quite coherent what Roman finds in his models. The geometry is more important than the material. Finally, and this is like what I've been looking literally like the last month, is how to describe these variations in timbre. Because what I would like to have is, I change the design and I have a tool that tells me my instrument is going to sound more bright, more mellow, more whatever. And if you take the spectrograms and compute the mel frequency depth coefficients, you can see that they nicely cluster in different parts for each instrument. And this kind of clustering is like perfect for data-driven analysis. Because you see that one color is here, another color is there. You can understand how the geometric or material variations in the design of the instrument are varying the way the timbre changes. You can do this with perceptual experiments. I would love to do it with Claudia, but I think it's so difficult to have reliable data from humans that somehow I have more faith in the computer understanding the timbre. And that's it. Thanks a lot. The team, it is a collaboration between a lot of people. Carolina Espinosa from Chile, with Emir, who was his master thesis. Matthias, master thesis in Polini. The violin, it's David Salvi, who is a PhD in Polini now. Daniel Baeza in Chile, my ex-boss. Alex Brachler in Stuttgart doing the experimental model analysis. And Giacomo and Ricardo are Polini students. And finally, sound synthesis by Mark Rao in Stanford. That's it. Thanks a lot. Questions? Not yet, but exactly that's what we want to do. Yeah, because so we use this to synthesize the sound, but the neural network can predict the amplitude and the frequency of the first 5 peaks. So we could make a model of this, and see how it sounds. So, but we haven't done it because the Mark's algorithm is not so easy to use, so we cannot connect them. He has to run for each one of these files. No, they both are these single layer, fully connected network. Yeah. When we do for rectangular plates, if we want to compute the amplitude, we need 2 layers, 2 layers. But for the complete guitar, it's somehow simpler. Probably if we vary the material parameters or the geometry of the whole instrument, we're going to need a more complex thing. But yeah, at the moment, like this very simple number works.
Can you show the device with the large set variations? When you make lots of variations?
This one? Yeah.
Speaking about when you make the variations, you can have and change the order of the notes. And probably you're not comparing the same notes.
I mean, we look at that, and usually it's the same notes. Yeah, they don't change that much because you cannot change the geometry that much that it does. And actually, I skipped the slide. It says like you fix the frequency, the modes fix themselves. They are like the Mach values of the different geometries are quite similar because the variation of geometry that something still looks like a violin, it's very small. So the modes don't change that much.
Yeah, how many variations?
By hand. Wait. This is, let me, for the Archtop guitar, it's compiling, sorry. Okay, there it is. Okay, well, that's the variation in stiffness for the top plate. It's a factor 2 between the minimum and maximum value, but we just do a Gaussian with a 25% spread. So that gives us, I mean, from the experimental values we've seen, the variation in stiffness is a factor 2. So just to be sure, we go like, this for the neural network of the guitar, actually it's 270. It's a weekend of simulation. Yeah, and it's for the, let me go back to the violin. For the violin, because when I first faced the problem, I said like this is very difficult. I need thousands. And we did that data set is probably 2,500 violin top plate. But then we just like started to reduce the number of data points in the training set, and around 500 it worked, probably even less. So it's a trial and error.
Any more questions? Some questions from people on Zoom?
There's a chat. No.
It's okay.
Okay.
Okay, well, thank you very much.
Thank you for the invitation.